Hello, George Romanic here. Welcome to Fundamentals of Weather and Climate playlist. In today's video we are going to discuss the reasons the Earth has seasons, and it has to do with the characteristics of the motion of our planet around the Sun. It takes 1 year for our planet to make one revolution around the Sun. More precisely, it takes 365.25 days. And when we add this 0.25 4 times, we get one extra day, and that is the reason every fourth year is leap year. And every fourth February has 29 days rather than 28 days. Now, the trajectory that our planet makes while revolving around the Sun is not perfect circle, but it is an ellipse. And the Sun is in one of the focal points of that ellipse. So if here is the Sun, S, then our Earth perhaps revolves around the Sun like so. And clearly there are 2 points that are of interest. One point is here and another point is here. This point is clearly the point when the Earth is furthest from the Sun, and this happens on 4th July. And this point is known as aphelion. And the distance between the Earth and the Sun at this point is 152 million kilometers. You know from chapter 2 that the average distance between the Earth and the Sun is 150 million kilometers. And there is this point over here when the Earth is closest to the Sun, and this is happening on 3rd January, and the distance is 147 million kilometers. And in this picture, the way I draw it, the Earth is revolving in the counterclockwise direction when looking from above, so to speak, and above means from North Pole. Now, you can already see from here that this change of the distance between the Earth and the Sun cannot be the main reason for the seasons, because when we have winter in northern hemisphere, the Earth is the closest to the Sun, and when we have summer in the northern hemisphere, the Earth is the furthest from the Sun. So something else has to control the seasons, and that something else are 2 factors. One is the angle that solar radiation strikes the surface of the Earth, and 2 is duration of sunshine at different latitudes, and this is what we want to discuss in the next segment of this video. Consider 3 sun rays that are traveling like so. And in first case, they will encounter this surface that, as you can see clearly, is perpendicular to these sun rays, and we indicate that as so. If we count how many sun rays is hitting this surface, clearly it is 3. And the surface is perpendicular to the incoming solar rays. However, if I take this same surface of the same length and I incline it like so, then you can see that this sun ray will still hit it. This sun ray will still hit it, but this one will miss it. How many sun rays is hitting this surface that is the same length of this one? Answer is 2. So we would say that intensity of radiation on this surface is smaller than the intensity of radiation on this surface. And the amount of solar radiation is unchanged, but what is changed is the orientation of this surface with respect to the incoming sun rays. As you can see, here orientation is 90 degrees, but here orientation is some angle alpha, which is less than 90 degrees. If I incline this surface even more, then you will see this sun ray still hits it, this sun ray will miss it, this sun ray will miss it. The intensity of radiation is 1 sun ray hitting this surface, and the angle alpha is even smaller. And of course, in the last case, if I make this surface horizontal, then notice that all 3 sun rays will miss it. So intensity of radiation on this surface is 0. We can also define this more technically, of course, in terms of flux. In this case, flux is 3 sun rays per the area of this surface per unit time, usually 1 second. In this case, flux is smaller. It is 2 sun rays per the same area of the surface per 1 second. Here, flux is even smaller. It is 1 sun ray per the same area per unit time, and here flux is 0, because we do have the same area, we do have same unit of time, but there is 0 sun rays that are hitting this surface. This, to great extent, has to do with the seasons on our planet. Let us now apply this concept to the planet Earth, and you will see how that relates to the amount of radiation that different latitudes on our planet receive from the sun. Let us apply now what we learned in the previous slide to our spherical Earth. Here is the spherical Earth, and let us say we have these 3 sun rays hitting the Earth in the tropical region. You can clearly see that the angle between sun rays and the Earth's surface here is almost 90 degrees, which corresponds to the first case in the previous slide. If we have 3 sun rays, 1, 2, 3, hitting the Earth's surface somewhere here in the mid-latitudes, then you can see that the angle now is smaller. The surface is more parallel to the sun rays than in the tropical regions. And finally, if we have these 3 sun rays, 1, 2, 3, hitting the Earth's surface in the high latitude regions, then the angle is even smaller, which means intensity of radiation here is higher than the intensity of radiation here, which is in turn higher than the intensity of radiation in polar regions. Now you might say, okay, I understand this, but still, how is this related to seasons? For example, why sometimes mid-latitudes have summer and sometimes they have winter? If this is the case, they should always be between tropical and subtropical regions, and temperature should never change because this orientation doesn't change. But the orientation does change throughout the year. And that is because in this figure, North Pole is not here. North Pole is actually somewhere here, and South Pole is somewhere here, which means that the axis of Earth's rotation is tilted towards the sun when we have summer in the northern hemisphere, and it is tilted away from the sun when we have winter in the southern hemisphere, which means the equator, 0 degrees equator, is like so. In other words, if this is the sun and the Earth is revolving around the sun, it is not revolving with the axis like so. It is revolving with the axis tilted. So when the tilt is towards the sun, we have summer in the northern hemisphere. And then as the Earth is rotating, the tilt is now away from the sun, we have winter in the northern hemisphere. And in these in-between positions, we have transitional seasons of spring and fall. gets even clearer when I put this picture in the context of the trajectory of our planet around the sun. So if here is the sun, and I will plot Earth here bigger than the sun to demonstrate my point. And let us say Earth is here. It is at the point that is furthest from the sun. But the North Pole is pointing towards the sun. And the South Pole is pointing away from the sun. Now, I hope you can see that, look, this plane over here is pretty much perpendicular to these three sun rays that I discussed before, and that's the northern hemisphere. Whereas another plane somewhere here in the southern hemisphere is now at very low angle with respect to the incoming solar rays. Of course, equator is somewhere here, 0 degrees. This is summer in the northern hemisphere. Tilt of Earth's axis of rotation is towards the sun in the northern hemisphere during the summer in the northern hemisphere. And the first day of summer is, of course, 21st June, which is also known as summer solstice. And then the Earth is now revolving around the sun, as I discussed several minutes ago, in the counterclockwise direction. And we get to this point over here, when the tilt is still like so. But now notice that the North Pole and the South Pole are not pointing away or towards the sun. The tilt is parallel to the sun. So we have what? After summer, we have fall. And the fall starts on 22nd September, and we call that autumnal equinox, when the length of the day and night are equal. And the Earth continues revolving around the sun, and now it is at the closest position to the sun, as we discussed several minutes ago. But North Pole is pointing away from the sun, whereas South Pole is pointing towards the sun. And lo and behold, notice that now South Hemisphere receives more intense radiation, because if I have these three sun rays, they are hitting Southern Hemisphere at almost perpendicular angle, and another three sun rays are hitting the Northern Hemisphere at very low angle. This is winter in the Northern Hemisphere, and winter, of course, starts on 21st December. And then the Earth continues revolving around the sun in the counterclockwise direction, and it finds itself here, and we have first day of spring, beautiful spring season, which starts on 20 March, and the Earth then continues revolving, reaching the summer season. 20 March is known as vernal equinox. And again, the angle of Earth's rotation with respect to this plane of revolution around the sun is again inclined, but not towards the sun, not away from the sun, but so to speak parallel to the sun, and therefore we have transitional season of spring. And finally, what is this angle that I'm discussing? If this is North Pole, this is South Pole, then this angle with respect to the normal, and normal is normal of the plane of revolution, this angle is, as many of you know, 23.5 degrees. And 23.5 degrees, therefore, you see, relates to my previous lecture because northern latitude of 23.5 degrees is known as the Tropic of Cancer, remember from previous lecture, and the southern latitude of 23.5 degrees that is known as the Tropic of Capricorn. And you can therefore see that when we have first day of summer in the northern hemisphere, because of this inclination of 23.5 degrees, Tropic of Cancer receives the highest intensity of radiation from the sun. When we have winter in the northern hemisphere, or rather summer in the southern hemisphere, then the Tropic of Capricorn receives the highest amount of solar radiation on that day, which is 21st December. This tilt of Earth's axis of rotation with respect to this plane of revolution is the dominant reason that Earth has seasons. And that affects the amount of radiation each latitude receives, as I demonstrated here clearly, I hope, but it also affects the amount of daytime that each latitude receives during different seasons. So the question is, how does this tilt affect the length of sunshine during a day? That's what we will discuss after I erase this whiteboard. To examine how the tilt of Earth's rotation affects the amount of daytime that each latitude receives, we will again consider a schematic of our spherical planet Earth with respect to the distant sun. And again, if we consider summer in the northern hemisphere, we just discussed, that means that the North Pole is pointing towards the sun and South Pole is pointing away from the sun. And this is the axis of Earth's rotation. And the Earth is rotating in the counterclockwise direction. That means that the sun is rising in the east and setting in the west. The reason is easy to understand actually. Consider me being the Earth that is rotating like so, in the counterclockwise direction when looking from above. And you, the camera, the observer, is the sun. Notice that my face is now in night. And as I am rotating in the counterclockwise direction, sun is over there, to my left, and that is the east. And now I am facing the sun, it's middle of the daytime, and now I continue rotating counterclockwise and the sun is setting. I am losing camera to my right, which is the west. And that's why the sun is setting to the west. Now this half of my body that is facing whiteboard is in night time. Yes, and this, my back, is in daytime. And now Earth continues rotating. Well, what I just explained means in this figure, this region over here is in night time. And this region, or this hemisphere of the Earth, is in the daytime. But notice that North Pole, in this case, is constantly facing towards the sun. So some region around North Pole, let's say this region over here, will constantly have daytime because the incoming solar rays, let's say those three rays that I discussed, will hit this region no matter whether we are in officially nighttime or daytime because of this inclination. And you know from my previous video that this region is north of 66.5 degrees. Similarly, there is a region close to the South Pole where we will consequently have 24 hours of nighttime. And that region is south of negative 66.5 degrees, or 66.5 degrees south latitude. And of course, somewhere here is the equator. So this figure therefore demonstrates that while the tilt of Earth's axis of rotation, which is 23.5 degrees, affects the amount of solar radiation that different latitudes receive, it also affects the duration of sunshine at different latitudes. When we have summer in the northern hemisphere, each latitude will receive at least 12 hours of sunshine, and each latitude over southern hemisphere, when we have summer in the northern hemisphere, will receive less than 12 hours of sunshine, and this latitude south from 66.5 degrees latitude south will not receive any sunshine, and it will be in 24-hour nighttime. And this is how the tilt of Earth's axis affects both intensity of solar radiation as well as the duration of daytime. There is one more effect that is important to mention, and that has to do with the Earth's atmosphere. These two effects that I discussed, namely intensity of solar radiation and daytime duration, with respect to this tilt of Earth's axis, are the so-called astronomical parameters. But now it is also, I hope, clear that this geometry also affects the radiation through its interaction with the Earth's atmosphere. Namely, what I want to say, if this is the thickness of the Earth's atmosphere, then notice that the amount of radiation, the distance that sun rays travel through the atmosphere over here is, let's say, this black line. But the distance that sun rays travel through the atmosphere over here in high latitudes is larger. Namely, it is clear that yellow line is much longer than black line. And that means that the intensity of radiation that is reaching the surface, not the top of the atmosphere, is larger in lower latitudes. Because if this distance here is large, that means there is larger probability that sun rays will be backscattered into the space or absorbed somewhere here in higher regions of the atmosphere and therefore do not reach the surface of the Earth and hit the Earth's surface. Whereas here, where the distance that the sun rays have to travel to the atmosphere is shorter, means that the probability of sun rays being backscattered into the cosmos or being absorbed in the higher regions of the atmosphere is lower, and therefore more radiation is hitting the Earth's surface. This is also very important. It is also a consequence, as you can see, of this tilt of Earth's axis, but it has to do with the tilt of Earth's axis coupled with the fact that our planet has the atmosphere. So now you can see that these parameters together result in Earth having seasons. Please like video, subscribe. Most importantly, please share video with other people so they can also learn why we have spring, summer, fall, as well as winter. Until next video, goodbye.